Okay, maybe you've heard of the number E. I want to talk about the number E. Now, it's not the definition, but the approximate value. E is about, if we round to maybe 3 decimal places, E is about 2.718 or so. Now, there's a number of different ways we could define this number E. We could say if f of x is equal to the natural log of x, then E is equal to f inverse of 1. So basically the inverse of the natural log function, plug in 1, and you get this number E. We could define, let's do that. We could define a different function. Let's say f of x is equal to the hyperbolic sine function plus the hyperbolic cosine function. And if we take, again, if we plug in 1 to this function, well then E is equal to f of 1. Let's see what else. We could define E as a convergent series. This is something you'll come across in Calc 2. So let's say E is as n varies from 0 to infinity of 1 over n factorial. That will give you E. We could define E in terms of a limit. E is equal to the limit as n goes to infinity of 1 plus 1 over n to the power of n, which is also equal to, and we could write this limit in a couple different ways, the limit as n goes to 0 of 1 plus n to the power of 1 over n. Now, for the purpose of what I'm about to do, let's focus on this definition of the number E. This is the one that's going to be useful in our derivation of the formula, the derivative of e to the x is e to the x. There are only 2 functions defined over the real numbers that are their own derivatives. One of them is a trivial function, y equals 0 or f of x equals 0. The other one is e to the x. So let's look at the derivative of e to the x. Well, the derivative of a function is equal to the limit as h approaches 0 of f of x plus h minus f of x divided by h. Okay, so here's our limit definition of the derivative. So let's apply this to the function e to the x. So that's the limit as h approaches 0 of e to the x plus h minus e to the x, all divided by h. Now, the limit is as h approaches 0. So the limit doesn't affect x. So let's see if we can pull that x out. So we could rewrite this as the limit as h approaches 0 of e to the x times e to the h. So that's e to the x plus h. We have a minus e to the x all over h. So when we factor out this e to the x, we could factor it all the way outside of the limit because it doesn't contain the variable h. Okay, so we have e to the x times the limit as h approaches 0 of e to the h minus 1 over h. Now, if we're proving this formula, if we're proving this derivative formula for e, we have to show now that this limit is equal to 1. But right now, it's still a question. All right, so we have to apply a little bit of mathematical trickery at this point. We're going to do a substitution, which allows us to incorporate this guy right here, this definition of E. Okay, the limit is n goes to 0, 1 plus n to the power of 1 over n. Okay, so how are we going to do this? Well, let's start with n. So let me use blue here. Let's start with our substitution. N could equal e to the h minus 1. All right, and now we have an h on the bottom, so we want to get rid of h. We want to bring in the n and get rid of the h. So if we let n equal the numerator, e to the h minus 1, now we could solve this equation for h. And we could solve this equation using the natural log function. Let's add 1 to both sides. So n plus 1 is equal to e to the h. And now, if we take the natural log, of both sides, ln of n plus 1 equals ln, let's do it this way, ln of n plus 1 equals ln of e to the h. Well, that gives us an h on the right and an ln of n plus 1. So we could plug this in for the numerator. We could plug in this for the denominator. And now notice from this first statement, n is equal to e to the h minus 1, as h approaches 0, that also implies that n approaches 0. So as this h goes to 0, that goes to e to the 0, which is 1, so you get 1 minus 1, which is 0. So as h goes to 0, n also goes to 0. Okay, so let's apply our substitution to this limit. Okay, so we have e to the x times the limit as n goes to 0, because remember, as h goes to 0, also that means n has to go to 0. The numerator, the e to the h minus 1, we're just going to call that n. So it's just a change of variable. N is just a placeholder for e to the h minus 1. And on the bottom, we have the natural log of n plus 1. Now, what I want to do is apply the natural log property. If you have a multiple out front of a natural log, that's the same as the natural log of x to the c. Okay, so we're going to take this property we know of logarithms and see if we can apply it here. So the way we're going to apply it here, let's take e to the x times the limit as n goes to 0. And instead of n in the numerator, let's bring the n to the bottom. Let's bring the n to the denominator by taking the reciprocal of the reciprocal. So a 1 over n on the bottom is the same as an n on top. Okay, so we have 1 over n times the natural log of n plus 1. Natural log of n plus 1. Now I'm going to scroll back up a little bit. Is this starting to look similar? Because if we're going to apply this formula I have in green over here on the left, and we bring this 1 over n up as an exponent, well, it's starting to look like this guy, this definition of E. Okay, so we could take this 1 over n and bring it up as an exponent. Okay, so we have e to the x times the limit. I'm going to just put the limit in red for now. The limit as n approaches 0 of 1 over the natural log of n plus 1 to the power 1 over n. Now, this limit's really only affecting n. It's not affecting the natural log function. So what we could do is we could put this limit inside the natural log function. And I think this should do it. So we have e to the x times 1 over the natural log of the limit as n goes to 0 of n plus 1 to the power 1 over n. Okay. So by putting the limit inside, well, now we have the definition of E. So this right here, that equals E. So we have e to the x times 1 over the natural log of e, which is e to the x times 1 over 1, which is e to the x. And this is what we were trying to prove. If we scroll back up to the beginning of the problem, we started here. We wanted to prove this derivative rule, so step 1 was to apply the limit definition of the derivative, and then we applied a little trickery here with our substitution we had in blue, and then applied one of the definitions of the number e, and used the fact that the natural log of e is equal to 1. Okay, so that is it. That is why the derivative of e to the x is e to the x. And like I said, there's only one other function whose derivative is equal to itself. We have the derivative of e to the x equals e to the x, and the derivative of 0 is 0. And that's it. Those are the only two functions whose derivative is equal to itself. Okay.